landscape. And like as we've heard a lot the past few days and in general in the communities, Calabi-Yaos are very nice, geometric string constructions are very nice, but they do lots of our heavy lifting on everything we kind of want to understand, whether it's swampland and trying to understand swampland conditions, swampland like constraints and general things about string theory, not even going into quantum gravity. They're a lot inspired by geometry, whether you're doing QFT or you're doing string pheno, or you just you care about like landscape or standard model physics or whatever you really care about. Usually Calabi-Yaos are pretty nice to work with, but we've put too much work for these guys. And it would be nice if we can help out and understand also like what other types of constructions can tell us about interesting questions. So if this big tree is our different sort of geometric constructions, including constructions that maybe could be seen in a more target space and geometric structure, then I can have a little tree here where it will have the non-geometric guys. So this is what I'm going to be talking to you today. And I will be interested in both discussing these, but also connections with geometry. At the end of the day, we do think that things are connected in some nice way. So it would be nice to be able to understand these corners in a more connected way. So let's go to 6D minimal supergravity theories. So as a first example, these guys have 8 supercharges, and they have a supergravity multiplet, tensor multiplets, vector, and hyper, and they just have tensor branches and Higgs branches, because only scalars appear here. Because these are chiral theories, there's a lot of constraints coming from anomalies. So they're pretty much very well constrained. And I'm not going to cite a lot of papers because there's too much. But there's a lot of ways to understand how these conditions restrict your theory. But what I want you to focus here is that if I have a choice for these coefficients here, these A's and B's that are actually part of my charge lattice, they have to satisfy certain relations to cancel anomalies. And if I know the matter, then I know these intersections, these inner products. Okay, so if I have the full 6D supergravity landscape, then one thing I can say, as we've discussed a lot about universality, I will be conservative and just say, we don't know if you have universality in 6D, but at least a large class of these theories we know that are string compactifications. Okay, and inside this string landscape, a large class that we know are also Calabi-Yau landscape. And in particular, a very large class that we understand is F theory on elliptic Calabi-Yau threefolds that give you a lot of interesting theories. The usual stories that you have the 3 branes wrapping curves on the base that give you different tensors and strings in your theory. You have non-abelian gauge symmetry associated to Kodara singularities and stuff. And there's a nice map between these anomaly coefficients we just saw, this minus A with the canonical bundle of the base, and these B's with the classes, the curve classes in the base. And there's something called the Kodara condition, which kind of tells you, how can I put different types of singularities together to have a consistent elliptic vibration. Okay. So one can wonder whether, for example, I can understand this kind of condition. What does this tell me from a supergravity perspective? I mean, from supergravity, these charges are gravitational instanton charges and gauge instanton charges, so they have a well-defined way to understand them. And then you can wonder if these are related this way. Could it be that some similar relation, I wrote it in terms of an inequality where J is either the Kähler class, if you're doing Calabi-Yau, or the scalars in the tensor multiplet, if you're just doing supergravity. And for example, they give you the tensions of the strings, and you can ask whether you can have some similar condition to be true. Actually, in 8-dimension 16 supercharges, you do have a similar condition that was shown to be satisfied from bottom up. So you could wonder whether there's something true here. Maybe it's some kind of conservation of instanton charge in a gravity theory or something like that. Okay, then the next question, I guess, here is, okay, so one issue here is that we always get one guy for free, and this is what we call the universal hypermultiplet. So the thing is, how special is this universal hypermultiplet? Is it something that is something very physical, or an artifact of our compactifications, because you always get one neutral hyper controlling the volume of the base in these constructions? However, if you check the anomalies we saw earlier, there is nothing wrong with just having no neutral hypers whatsoever. So you can ask if I can realize such a theory. And the thing is that there's nothing, and this is what I'm going to talk about, that there's nothing in 68 supercharges in particular that I need to have this universal guy. Okay, so a question you could ask then is that, okay, if I have this universal indice theory models, is there a way that I can go on this Higgs branch and it can be charged at some point? Okay, so I'm going to go back to the 80s here with George Michael and the song that was on the Billboard that year, A Different Corner, and talk about a different corner around here. And this will be basically exactly something from that year, which was the asymmetric orbifold constructions. This is old news, it's not new things. But what is new and interesting is that you can find still new stuff by old methods. And that's what we're going to do here. So we're going to be asking whether I can have in 60 this non-neutral hyper, whether I can have theories that violate this condition that all geometric theories, I mean, I only spoke about F theory, but you can do other geometric orbifolds, brane constructions, and you can see that nothing violates this. More precisely because you can think of it in a duality frame, you're going to end up in F theory, and they're kind of satisfied. Okay, so you can ask this question, and then you can also ask whether these guys can be connected to the geometry. Which basically tells us that, you know, if I was to think about, and at some point I was thinking about whether this is a Strawman condition or not, but as I said, some kind of conservation of instanton charge and stuff, whether our intuition comes from a lamppost by just studying specific things we know how to do, or whether there's more beyond that and, you know, we're in a stringy lamppost situation. Okay, so just a very short review. If you just want to do an abelian orbifold, you don't have to do too much. You just pick your favorite string theory to A to B heterotic, and then you pick your favorite even self-dual lattice here for your momenta, and you can compactify. And how we do this is to create an orbifold is that we pick some lattice automorphism, which we say tags as an automorphism of the lattice in that dimension, this crystallographic action. And then once I know all the possible actions, then I know the symmetries that I can use. So I can use certain twists and certain shifts along the lattice. And this is how they act on my Hilbert space, the twists and shifts, and then find new theories. So this is old news. It's not something most of you have seen, but in the symmetric case especially, we know you have Calabi-Yau's that have these nice orbifold points and stuff. And if you choose the left and right actions to be not the same but different, then these are the asymmetric orbifolds. And the reason that you can think of them as non-geometric is quite simple, because when it's symmetric, you really have a way to think about how this acts on the coordinates of the target space. But when it's asymmetric, it is not as obvious, although there is something you already know, and it's T-duality, that you know it acts asymmetrically, and then if you do it twice, it is a symmetry of your theory. So you kind of already know an action of that form. So this is what we're going to be focused today. Okay, Okay, so let me give my first example. So we have lots of, yeah. Sorry? Yeah. So, I mean, the way you usually, I mean, I didn't put details. It's like you consider the untwisted sector, which is your invariant states. And then when you want a partition function to be modular invariant, you can do modular transformations to see that you actually need more. So, and this is the twisted Hilbert space. So you have strings that are closed up to G action, and this gives you the twisted partition functions that you have to add, and then the total thing is modular invariant. Yeah, for example. Okay, so here we picked a D4 lattice, and we did a very simple twist where we choose to break all of the right moving supersymmetry by -1 to the f, which we saw earlier today, and we do a Z2 to break the other half of the left moving supersymmetry. In this case, so we can end up in 8 supercharges. And you can check actually that the spectrum of this theory, even though it seems very simple, in fact has 9 tensors, 12 U1s, charged matter, and no hypers at all, neutral hypers at all. So this is not something you would get from an F-theory construction. As simple as it is, it's a new theory that I didn't know before, that you have no neutral hypers in 16. And what is interesting is that now, though your string coupling usually lives in these hypers, it actually lives in these tensor multiplets. Although this is not entirely surprising. I mean, it is surprising maybe from the type 2 picture, but you do also know theories that have string coupling in vectors and stuff, and this usually come from heterotic construction. So it would be interesting to know if there's a relation to these models. Okay, so we're...
I'm a bit confused. Theory with 9 tensors and 12 hypers is anomaly free.
Excuse me? No, this is also anomaly free. You need to plug in the charged matter. Yeah. Okay. So, what was I saying? Oh, yeah. So, and yes, please, if you have questions or I'm confusing anyone, please ask me. So, okay, so we definitely have one model here with no neutral hypermultiplets that is sitting in here. Now, the next question can be, again, can we satisfy this? And the thing is that, yes, in that model that I just talked about, the Kodaira condition is also satisfied. However, if you do now a heterotic asymmetric orbifold, again, we're looking for the same thing, no neutral hypers. You can pick your favorite lattice again. We just took an A2 plus A2 and the 2 E8s. We took a right-moving twist by this Z3 action. We did a shift for the heterotic lattice and find 8 supercharges again, and the spectrum of this form. You have one tensor, large gauge group, lots of charged matter, and no neutral hypers again. Great. And then you're going to ask again the same question, but here actually you see that the matter I just described over here does not satisfy the Kodaira condition. So this gives me the first example that I know that actually this condition is not as generic, even though constructions we knew satisfied it. So that is interesting by itself to be able to wonder about more types of constructions before we think about attacking general questions. And then what is interesting is to ask whether there is a connection to geometry in this picture. Well, in fact, if you Higgs this theory, you can you have so much charged matter and you Higgs the theory, you actually find one tensor, E8, no charged matter, and 492 neutral hypers. And some of the F theorists in the crowd or even heterotic people know this model. And this is familiar because it is the F theory model with a base F12 that just brings you the E8 model. Now you can ask me, why do I think this is the model? I mean, the massless spectrum is that way. It doesn't necessarily have to be, and that is true. But at least at the massless spectrum, it looks like it could be related to this, which I'm going to come back to. Okay, so one more thing is that for now, let's assume that we have this Higgsing to this Calabi-Yau threefold with base F12. then we also know through duality we can connect this to a heterotic model on K3 with instanton number 0 and 24. Okay. Now, if you consider the theory on a circle, what is quite nice here is that actually you can see this in the same moduli space. So what is going on here is that the heterotic asymmetric orbifold that we just did, that had no neutral hypers, and these other theories are part of the same moduli space. And then you can ask, for example, if I was to go from this theory to that theory, what am I actually doing? So what I'm doing is that I'm actually going on the Higgs branch in a way of the base hypermultipled, and I'm going to a very small volume regime and strong coupling, and I have this kind of conical-like transition to this heterotic asymmetric orbifold. And of course, from that picture, it's not obvious why this should be, because from the F-theory perspective, this is a strong coupling, so it's not something you can actually trace. But it's very suggestive. But you can be a little bit smarter than this, and these people also were, and actually see that this model here, you can see it from the heterotic picture itself. So there is actually, on this model, a self-dual radius point where the string theory is perturbative, and you can end up with the same spectrum as this asymmetric orbifold. So now you actually have a perturbative description of what is going on from the F-theory picture in the strong coupling. So it is very suggestive now that, in fact, this picture is correct. And you can have these extra transitions at these non-geometric points that your geometry breaks down, and you can treat these scalars also as part of your moduli space. They can undergo transitions, etc. And this shows a very nice connected picture of this model. In fact, you can go and do more. So this is the original theory I talked to, the type 2. This was the heterotic I just discussed, and I give you 2 more heterotic models with some twist and shift. For example, this model, we're doing a CHL-like autoautomorphism between the 2 E8s, and you get a nice spectrum for these theories. Here with charged matter, none of them have neutral hypers. I just didn't write the charged matter because it's long. And the interesting thing is that none of these guys satisfy the Kodara condition, in fact. So actually, it's more generic, getting these heterotic models not satisfy the Kodara condition. And in fact, if you Higgs all these models and play exactly the same story, in these, you get exactly the Calabi-Yau with base F12, F0, and F3 from the F-theory picture. We know the duals in terms of heterotic theory. And again, you can play the same game and go to the self-dual point in the K3, where you actually find the non-neutral hypers asymmetric orbifold point, which is really nice. Here we are lucky, and we have a nice perturbative description of this dual frame where F-theory was actually strongly coupled. Now, in this case, if you were doing exactly the same thing, you would have found Calabi-Yau with base DP9. This is no longer a perturbative heterotic string. This is actually, you have to go to the Hojava-Witten or M-theory description of that, because, or you can think of it in terms of K3 with NS5 branes. You can maybe hope that, in fact, this sort of self-dual points still exist when I add this NS5 branes, but it's not so obvious to actually go and find that theory. But it is very suggestive. So now we have all these theories. And one more thing is that, as we saw, all these things have this M theory on the Hojava-Witten times K3 description. And we know that the instant numbers are related to how many branes I have in each side of the interval or in the middle of the interval. And we know that we can just push them on the boundaries, bring them in. And from the F-theory picture, it corresponds to a blow up, blow down, or going from a tensor branch to Higgs branch transitions. So then you can, in fact, connect also all these theories this way as well, through tensor branch transitions. Okay, that's great. In fact, I was telling you that you can do this in one dimension lower, right? Because I needed I needed them to be part of a moduli space. So in fact, all these theories gives you this 5D Coulomb branch with U1 to the 22, and this gives you, if you turn on some Wilson lines, So you can get rid of the charged matter, and then you have a U1 to the 14 over here. And this is the connectedness of the string vacuum I was just talking to you about, where you have the Coulomb branch we just saw, this one, being related to the Higgs branches of the F0, F12, and the P9 models I showed you earlier. These are related through instant-on tension branch transitions, and it shows you how now all of them are part of a single sort of moduli space in the lower dimension theory, and you can go to these asymmetric orbifold points just by doing simple geometry. Okay, now you can continue asking that question to lower dimensions, and in fact, people have already studied, and the paper has already come up, where they studied free actions in 5D, and we wanted to also understand what kind of theories with no hypers at all now in 5D you can get. As I said, they already did some here, and we're doing as well, where we also do freely acting orbifolds, and we add a shift. So you do a normal orbifold, and then to get it freely acting, you add a circle and you shift along that circle, which leaves all your twisted sectors. Okay, and this is a table of the theories we got. We got rank from 2 to 22 from all models we tried. I mean, we just gave you some representatives, so we don't give you over and over again the same ranks of the models. But what is interesting here is that the rank is even, which was also noticed in the other paper. We couldn't actually beat that. Where's the reference? There. Okay, the rank is even, so we had the same conclusion, and that the rank is bounded. An interesting thing is that for all these no-neutral hypers, the rank is bounded by the same bound that is true for 16 superchargers that we talked earlier. Is there a reason why these no-neutral, no hyper theorists sort of act like more 16 superchargers? Know that it's not just freely acting. Some of these models were not freely acting, the ones that we discussed from 60. We still couldn't beat it even with not freely acting theories. So it is interesting to know whether this is a general thing or it is a very specific thing to the maybe perturbative string landscape we're discussing. And of course, that comes back to what Miguel said we're discussing earlier too, for R equals to 0. This is the 5D pure supergravity. It's 5D, n equals to 1, 8 supercharges, R equals to 0. Does this theory exist? This is what we were trying to get and obviously couldn't. Well, we couldn't get it this way, and we actually argued that you can't get it. And I mean, it's very simple why you can get it directly is because you have no scalars, and a perturbative string theory will always give you at least one. So it's not a perturbative string theory. You can ask whether you can get it from a 4D with one vector multiplet. Well, we argue that you can't, at least for abelian orbifolds. So maybe you can be smarter and find a theory that can. But you can wonder that maybe it comes from 3D. So the idea of the 4D with one vector is something that attacks like M theory. So you take type 2 and the strong coupling, it decompactifies to this with no scalars. You could ask maybe in this case it's a 3D model and not a 4D model that decompactifies. So what you're looking for now is a 3D model with two with the right amount so that you have two scalars to decompactify potentially. And we had taken E6 lattice with certain twists. And the question is, could this be our theory? Because we find exactly the right spectrum that you have for that theory. Now, we know the emergent string conjecture will tell us that the theory should decompactify the infinite distance limits or be a string limit. So, I mean, if you're lucky enough and it decompactifies, then that's your theory. But for example, if you take the radius of the circle, you get extra supersymmetry, not interesting. But at strong coupling, we don't know what is happening, and you would need to know the incident corrections to actually know. But you have a potential example with minimal amount of matter such that it could potentially decompactify to your 5D pure supergravity that has no scalars at all. Okay. And I will conclude with a couple of things that, one thing actually that I'm thinking also about now is, as I just discussed, we discussed abelian orbifolds with these crystallographic symmetries at TD. There's some more general framework called quasi-crystalline compactifications, where you actually consider automorphisms not of your target torus, but rather than of the lattice itself. So you want automorphisms that are crystallographically in 2D dimensions and not D dimensions, and this gives you more general orbifolds. The way you do it has kind of the opposite way. You first sort of find these automorphisms, and then you build the self-dual lattice that you want to have to be consistent. And these are, for example, some preliminary theories that we get. It's not, I didn't see something super interesting in the sense that we already know. What is interesting is that these are different types of constructions, and you still get, for example, this 60 theory with 21 tensors, the chiral theory. You get the equivalent of F theory on a Calabi-Yau with DP9 base, but from this quasi-crystalline compactification. And for these freely acting orbifolds, you can have potentially a string island in 60. So this is a 5D with one vector and 16 supercharges. It's normal to expect that this would decompactify. Then you would have another string island from this quasi-crystalline picture. Could be connected to the already known to the already known string island, but it's not obvious. And you have a lot of non-supersymmetric examples, which they all have tachyons, unfortunately, unless you do the free action, which we're doing, and then at above some radius, you know that you won't have a tachyon. But I would say that this is not extremely interesting in the sense that we know examples like that. But what is interesting is that you have a minimal amount of scalars. For example, this is with 2 scalars and no tachyon above certain radius. So you have a very minimal amount of matter in these theories. And well, we have a whole list of these. So why they're called quasi-crystallines? Because exactly they have your P left and P right actually are not what was I talking? They're not. They're never 2. They're either 0 or they're rational numbers. So it kills a lot of massless modes. That's why we got so many small amount of massless modes. And this is the picture of these. This gives you actually rational CFTs. So that's why sort of it's interesting to see how these irrational CFTs are connected to the rest of the moduli space. And to summarize and discuss some general things is that, as I said, these non-geometric models and things beyond geometry are great for Swampland conjectures, trying to really, I want to be able to understand the string landscape first to sort of try to understand more specific aspects of what I think is universal. Understanding boundaries of the landscape, string landscape. It would be nice to know if that 5D pure probability exists, if you can argue that, for example, that it does decompactify. Looking for more examples to try to understand if you can have other not supersymmetric theories, which are tachyon-free. And of course, we have a whole discussion, so I didn't want to steal the thunder with too many questions. But I think it's interesting to explore this and explore different aspects of maybe these non-geometric string constructions beyond this also orbifolds to see what else we can have. Yeah, thank you very much.
Thanks. Could you explain again this transition, this geometric transition, how you related these non-geometric theories to the elliptic fibration? Are you saying that you shrink the base and then do the Higgsing? Is that what you
Yeah. So basically, the thing is that from that perspective, you expect the model Higgs is there. So you expect that in the one-dimensional lower, it will be a Higgs-Browns transition that is happening, that you get to the asymmetric orbifold. But because it's a strong coupling in F theory, it's not obvious to argue for it. But because in that case you have a heterotic perturbative model, you can actually do it perturbatively in heterotic and find that exact asymmetric orbifold from the K3 picture. And then if you were to trace it back and see what you did in F theory, because you have the duality, then what you actually did is that you shrunk the volume of the F theory base to 0 size, your neutral hyper got charged, which was your string coupling, and you ended up at that non-geometric phase.
And that doesn't give an SCFT in 5 dimensions, the shrinking of the base?
SCFT, what?
The shrinking of the base, does this in 5 dimensions, does this not give an SCFT, a 5D n = 1 SCFT?
You haven't decoupled gravity in that case.
Well, okay, fine. But apart from that, like that, but that's what you're doing. So you go to this point where you.
Yeah, you
Where
go,
you
basically,
would have
you're
the
treating it as another Higgs branch
Yeah, okay.
transition or complex structure deformation you could have done that you don't see from the geometric picture.
Thanks, Corey. Super nice talk and work. So I just wanted to ask, so you were mentioning you have the 5-dimensional model that would decompactify to 6 dimensions to give you string island, right? Why couldn't you just try and get the string island directly in 6 dimensions? Why did you go? It just means why you have to go down that route.
It's cheap. So because these quasi-crystalline things only are on even dimensions. So I have to do it on even dimensions and then do the free action and shift. So I needed to go directly there and then potentially up again.
Okay, thanks.
Is there a version of the story with gravity decoupled? Can you get like 60 degrees?
Well, I've thought about that, but it's not obvious to me. Actually, I want to bring that up in the discussion. It's not obvious to me how to understand these asymmetric orbifold points from a non-geometric construction. I don't know if people know, because at the end of the day, some of these, like take T-duality, you're kind of exchanging branes of different dimension. I don't know how to think about this with gravity decoupled. If I was to say that I have maybe a new kind of singularity that considering new time of CFT, I'm not sure. Actually, I wanted to bring it up in the discussion.
I don't see any more questions, so let's.
Thank you. Okay. It takes some time. Yeah, put it in your ear.
¿Ya uso cuando fuese 5 minutos o?
Yo voy a poner un cronómetro también. Voy a poner un cronómetro también, pero por favor. Is this this one?
Oh, the next speaker is Héctor Barra de Freitas.
Can you do full screen instead of presentation? Sorry about that. The full screen. Yeah. I mean, maybe quizá se hace así. From start. It's an automatic. O sea, también se puede dejar así, creo que se ve. Pasa que no, el PFA no sirve. no está actualizado.
You can switch to presenter mode and
Yeah, where?
next to the Zoom bar, like to the Zoom slide at the bottom right.
Zoom slideware here, no? Thanks. Thank you. All right. Well, I'll start by thanking Mariana, Alvaro, Nico for the very nice workshop and for inviting me to speak here. Very happy to be back here in Sacramento where I did my PhD. I'm going to be talking about, yes, non-supersymmetric strings and rank reduction. Most of the work for introducing this kind of thing was already done by Miguel and by Juri now regarding asymmetric orbifolds. So let's see what's the deal here. So the basic question is, how can we understand, let's say, the salient aspects of non-supersymmetric strings in simple examples? Okay, and this includes, so you can have in your mind the non-supersymmetric heterotic strings, compactified circles, and analogs of that. And here I'm showing you two pictures that are from this recent paper. By the way, this is work in progress and some work I did with Bernardo. But this is related to this work with Mariana, Sav, and Bernardo of compactifications of the non-supersymmetric heterotic strings. And what I want to show you here is like this. You can think of it as a moduli space classically, but of course you have a potential because the theory is non-supersymmetric, but still you preserve many properties that you see in supersymmetric strings, like for example symmetry enhancements. But of course now you have tachyons. This is a common problem. But see here, this is very nice. You have enhancements, and there are maximal enhancements here that they extremize the cosmological constant. This was shown by Ginsburg-Baffa. I didn't put the reference here, but this was shown by Ginsburg-Baffa back in the 80s. Okay. But now we have matter content because the theory is not supersymmetric. Okay, this is something I would like to understand for many theories. Another thing is I want to classify them. And why do I want to classify them? Well, because you keep constructing new theories and new theories and new theories, but do you know if you're finding the same thing over again? So if we have some classification scheme, then that would be good. So we can cut redundancies. And this is something feasible if we find relations among them. Okay. And the other thing is, can we see some inherited properties from supersymmetric strings? And here I want to talk about the duality. I will talk about it at the end of the talk, which is a kind of controversial thing, but it's fine. But I will restrict to spontaneous supersymmetry breaking, something like search reductions. So explain a bit more about that. Okay. So, and these are theories that descend from theories with system supercharges. That's why they are preserving so many nice properties. Okay, let's review the supersymmetric case. Okay, so if you have theories with system supercharges, as we saw in earlier, they have many nice properties. It allows us to study them in a very controlled manner. They can in particular be realized by taking the heterotic string and doing asymmetric orbifolds, like Juri explained. But in this case, we want to preserve supersymmetry, 16 supercharges. And you can also do it by breaking half supersymmetry in type 2 strings. Of course, there are many other constructions, like geometric constructions, type 2 and K3 and so on. But I believe they all have a asymmetric orbifold corner. There's a lot of evidence for this. And each one of those constructions will lie in a disconnected component of the moduli space that is characterized by the rank of the gauge symmetry. Okay. Now, if you go to a dual frame in 7 dimensions and 8 dimensions, like you take a theorem theory, you put it in a K3 surface, then every non-component of the moduli space is captured by freezing singularities. So you can freeze singularities on the K3, and you get everything that we know. And these frozen singularities, there was a bit of an explanation before what they are, but you can think also of them as generalizations of orientifold planes with positive charge. Okay. And when you have these frozen singularities, because you know you can freeze them, then you can do a formal mapping of the main component of the moduli space with full rank to those with rank reduction. Okay. This series with rank reduction, they exhibit other interesting properties beyond just classification purposes, like having non-simply laced gauge symmetries or higher levels in the gauge algebras and so on. So this mapping of the gauge symmetries was done for 8 dimensions in the heterotic string with respect to the CHL string in this paper by some authors that are here. And then I extended it with Bernardo to other cases with frozen singularities. Okay. Here, I want to show you this a picture in 7 dimensions of all the moduli spaces that we have. The red letter here is the rank. The letters here, they represent ADE, frozen singularities. And I just want to emphasize that we can start from here and go to every one of them using some special map. And here, just to remind you what is the form of these moduli spaces, the coset spaces, quotiented by some discrete symmetries, though I will not enter much into detail about this thing here. All right, if we go to 6 dimensions, we don't have any physical way of realizing a map analogous to this, but we can be smart and formally generalize the map looking at properties of these theories. And what we found is that actually the map has a nice action on the gauge symmetries, and it acts depending on the topology of the group. So anytime you have a gauge symmetry like this, you can think of the heterotic string. The 10-dimensional heterotic string with this gauge group is not a SO32, it has a set 2 here. And then you go to 6 dimensions. What you can do is say, well, this set 2, it defines an automorphism of the Dynkin diagram that you can then fold, and you get this group, which is not simply connected, and it's spin 17. And this defines a group in a different component of the moduli space. You see here very explicitly that the rank reduction is by 8, so this has to be the CHL string. Okay, so we recovered the CHL string using this kind of formal rule. There are other examples, like if you start from E6 times E6 times E6, and you have a set 3, this thing will act on each one of these factors and give you G2, 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 you reduce the rank by 12, and then this is set 3 triple. So it's another component of the moduli space. The point is that you can then think, okay, maybe I can do this in any way that I can, in any way. And I will, if I do that, I recover every known component of the moduli space, okay, and with 16 supercharged in 6 dimensions, and then I can predict others, which is what Miguel mentioned earlier. But here I want to be a bit more conservative because there is a class of compactifications that are only cyclic orbifolds, and those are better controlled. Non-cyclic orbifolds are not well explored, and the non-cyclic ones are those that you need in order to realize odd rank in 6 dimensions. So this is not part of the discussion here. Now, another very interesting property of these theories is that if you compactify them to 2 dimensions, you put them on a torus, so you're preserving all the properties, you compactify them to 2 dimensions, and you do variations of the moduli, you do some marginal deformations on the worldsheet, you can see that there will be points where the partition function will factorize holomorphically. So this is a cartoon of the moduli space in 2 dimensions. You always have these points here, where the partition function is of this form. And then you can say, okay, if the partition function looks like this, I have a potential for doing a classification, because this left-moving CFT, for consistency, it has to be a bosonic. In the case of heterotic strings, it has to be a bosonic CFT with central charge 24, and these things were classified as Schelecans back in the 90s. So, and if it's type 2, then you need C equal 12, and this has to be a theory with 24 real fermions and a particular choice of current algebra. And you can see some nice things about these tensor products in this relatively recent paper. Okay. So here, part of what I want to think also is that the Schelecans list, if you look at Schelecans list and then you turn the problem on its head, you can see that there are missing string theory constructions in 6 dimensions that would fill out this thing. And then we strongly believe that those theories should exist. Okay. Another very important point is that these CFTs, they are not just some tool to do classifications, they actually encode information about the 6-dimensional theories, and they encode every possible gauge symmetry that you can have in 6 dimensions. Okay, so that's an important point. I will explain a bit more about this later on. Okay, so this is the big picture in the non-supersymmetric case. Okay, I have a classification scheme for these things. And this includes any theory with 16 supercharges, 6 dimensions. Okay, so let's see about the non-supersymmetric case. Okay, the question is there an analogous story for non-supersymmetric strings? I think there should be one way or another, and the reason is simply that no supersymmetric heterotic strings exist. So these theories, when you look at them classically, as I said before, they look very much like the supersymmetric counterparts, at least classically. So they share so many properties, and since you can do all asymmetric orbifolds in the supersymmetric strings, you think maybe we can play the same game here, okay? And all the structure that I mentioned, there should be something analogous to it. Okay. There is a clue to realize this goal, and it's to remember that in 10 dimensions, the supersymmetric heterotic strings, they are given by bosonic CFTs with central charge 16. There are only 2 of them, E8, E8, the one with current algebras E8, E8, and SO32. So you can kind of have your classification in that sense. But the non-supersymmetric ones, they are related to fermionic CFTs, okay, which are less constrained. And you have 7 of them. So it follows that you have 7 non-supersymmetric heterotic strings. This relation was explored and treated very carefully in this recent paper. Oh, sorry. In this recent paper. So then the point is that, of course, if I'm going to play the same game as before, I need the classification of theories fermionic CFTs with central charge 24, which is a much more difficult problem. Okay, but fortunately, this was achieved very recently in the mathematics literature by Ho and Moller. So what they did there was basically do the same that Tachikawa and company did here for some fermionization procedure applied on the bosonic theories, but going up to C equal 24. And they find 969 CFTs of this type. They are arranged into 33 families. And each one of those families can be then associated to a 2-dimensional moduli space for non-supersymmetric heterotic strings. Okay. So let me explain this a bit more in detail. This picture here is central to all the discussion. So what does this represent? You have lots of nodes labeled by letters, and those nodes, what they are families of bosonic CFTs. Each one of those families corresponds to many points of factorized CFTs, and they in turn correspond to a moduli space of supersymmetric heterotic strings. So for example, this one here, A, is just take the heterotic string, put it on T8. You have 2-dimensional theory with 16 supercharges, and it's here. Okay. And there are many others, like the CHL string corresponds to this, which is a set2 orbifold, and then you have many other things, like the triples of triple foxes and strings, like every orbifold that you can get in high dimensions, it should be here, and it is here. So then we have links, and what those links represent are non-supersymmetric. So they represent here in the formalism of CFTs, they represent the fermionic CFTs that you can obtain from the bosonic ones. So there are 4 kinds of links. They are called 1, 1A, 2B, and 1, 2A, 2B, and 3 by Ho and Moller, and they are families of fermionic CFTs. So, for example, here, those like A1 here it will correspond to the O16 heterotic string compactified on a torus. Now, all the rank 16 heterotic strings are T-dual. So here is you think of those 6 non-supersymmetric theories that are all encoded here. Okay. All of these theories, the worldsheets, they are constructed using -1 to the f, like the shared source reduction, the usual shared source reduction, but you accompany it by an automorphism of the charge lattice of the theory. And then there are different kinds of shifts that you can do. I'll explain in a second. So the conjecture that I have, and I'm very confident of, is that all of these theories, the non-supersymmetric ones, will also uplift to 6 dimensions or more. So it gives me a classification of those theories. Okay. And the intuition behind that is that to construct them in 2 dimensions, you can do that. And this requires outer automorphisms. And then those automorphisms, they have to uplift to 6 dimensions, and then you can apply them there to get the 6-dimensional theories. Okay. And so another important point is that if you take something like the CHL string, the charge lattice is more complicated than the Narayan. So you can shift in different ways because you don't have all the idea is this. You have a charge lattice that is not self-dual, so you have different kinds of vectors, and if you shift along those kinds of vectors, you get different theories. But doing that is very challenging. It's not that trivial. Explain a bit more in detail what each one of the letters mean. You have class 1 theories. I call it them class, not to use too much the mathematical jargon. So let's call them class 1. They are genera, but it's a class 1 theories. They are shared source reductions. So let's say you take the CSH string, you do a shared source reduction, you put it in a circle with antiperiodic boundary conditions for the fermions, you get B1, which should be right here. Yeah. Class 2B theories, they are like non-supersymmetric versions of the supersymmetric ones. So what that means, you have the supersymmetric theory, it's defined by some kind of orbifold, and then you attach an extra -1 to the F there. This will break supersymmetry. And a nice example of that is the so-called non-supersymmetric CSL string, which was constructed and studied very in depth by Nakajima this year. And there are those versions, you can find them but for many other supersymmetric theories. The class 3 theories, they do not involve shifts. So they're like the E8 string. The E8 string is here, it's B3. And the class 2A theories, they involve other kinds of shifts, and they're not much explored. But something that one can check is that the B2A will correspond to a shared source reduction of the E8 string. It's weird doing a shared source reduction of the E8 string because it's already non-supersymmetric, but you get another non-supersymmetric theory. And this fills the classification. So if you have a non-supersymmetric theory constructed along these lines and has rank reduction by 8, then it has to be here. Okay. How do you prove this? Well, you have to do a computation. So you need to compute the partition function of these theories that I mentioned here. Then you have to play around with it, do some deformation of the moduli, factorize it, and then match it with the data of the partition functions presented in this classification. And it works. Okay. Now, the classification seems to work fine, but what can we get from it? So, can we get spectral data of the 6D theories? Let me explain what I mean. If you have a heterotic string on T4, you have type 2 strings on K3, then it is a fact that every gauge symmetry is encoded. Let me restrict to non-abelian gauge symmetries. All of them are encoded in the 24 Naimayer lattices. These are the lattices that underlie the family of associated CFTs. I'll give you an example. So this is the Naimayer lattice 3E8. You write down the Dynkin diagram. You take out 4 nodes. This is the prescription. You take out 4 nodes however you want. You get something, some algebra. And this has a 6-dimensional realization. You do this for all the Naimayer lattices, you get everything. And this is valid for every other component of the moduli space. Now, you can ask if this is also the case for the non-supersymmetric counterpart, for the 16 on 16. It's a bit more complicated because you don't have 24 lattices, you have 273. Okay, each one of them corresponds to a fermionic CFT. But you can prove, starting from the knowledge that this works in the supersymmetric case, you can prove that it also works here, which is more interesting because you don't have only vector multiplets, you also have matter. You have matter content, so you have gauge bosons, you have matter content, and you have tachyons. You can have tachyons in these theories, and great part of the spectrum will be encoded in those lattices. An application of that is if you want to explore the space of all of these compactifications, you want to check for extremal points of the potential, then you can really make that job simpler here, though it's something to be explored. For the other non-supersymmetric theories, it's much more difficult to prove it, like analytically, but it seems feasible to do with the aid of computational methods. But it seems that all those supersymmetric aspects that we have are also here in this case, in this family of theories.
Sorry,
yes.
Why can't you remove nodes from one, 2 nodes from another, and 0 from the third?
You mean, sorry, you can remove any kinds of nodes that you want. You can remove.
Okay, so these are just 3 examples.
There are 3 examples
Okay.
from. Okay. Okay. Now, is there some? Okay. Let me go with time. Okay, fine with time. Rank reduction and duality. So I said it would be nice to have a rank reduction map in this non-supersymmetric series. I think it's a good thing to have because then you can very easily produce the spectrum of this series. But remember that those maps have a physical realization as frozen singularities or orientable planes, things like this. So if we had something here that we could prove formally, then it might have some physical meaning. Okay. Let's think about it just formally. The challenge is that since the spectrum has different classes, you have gauge bosons here, matter there, and each one is related to different subsets of the charge lattice of your theory, it really doesn't seem to make sense to take two theories and embed the content of one into another. How do you do this? It's not clear. Okay. And there's another problem, which is perhaps deeper, that, as I said, the rank reduction maps are meaningful as singularity freezing in MF theory, but I'm not doing M theory, I'm not doing F theory, I'm doing heterotic strings. It's perturbative. Okay, so we don't have such a dual so far. Maybe they don't exist, I don't know. In the non-supersymmetric case. And in general, there's very little known about string dualities, string-string dualities. There were some attempts at constructing them back in the 90s for the SO16, SO16 string, for type 0 strings, things like this. But it's really murky. It's not clear if these dualities actually work. So let me think here of a first step with these rank reduced theories. Maybe we can find an orientible that is dual to one of them. And I want to propose such a thing. Okay, and we start with the CHL string. Okay. So the CHL string, it has an orientible dual in 8 dimensions. So you take type 2 theory, you do an orientible, and you put, you usually would put 4 or 7 minuses. And this could be dual to the heterotic string on T2. If you then, and of course you need a number of branes to cancel the R tadpole, but if you exchange one of those orientable planes and some branes by an O7 plus, then you reduce the rank of the theory because you have less branes, and you get a dual for your CHL string. Okay. Now, in this special case, you can break supersymmetry by conjugating the RR charge of these two orientables. Okay. So you exchange these two guys by anti-orientable planes. Okay. Now you still have 87 branes, so they are not mutually BPS, and supersymmetry is broken, but you don't have a tadpole. So you don't have a 3-level energy, which is something that is usually in brane supersymmetry breaking constructions like this. And this is a model that was put forward by Kurdashev, Dudas, and Partouche in 21. I didn't put the date, but it's fairly recent. It's 21. Now, the spectrum of gauge bosons is not altered. Okay, you still have the same gauge bosons, but the spinors they are altered. And so they go now to symmetric or antisymmetric representations of your gauge group. And this is a fact of the spectrum. But the interesting thing is that if you take the CHL string and you break supersymmetry, this non-supersymmetric version of the CHL string, you get exactly the same behavior at all points in the modalized space here, except for the fact that now you don't have fermion singlets. Okay. So here in the symmetric antisymmetric representations, they are reducible. They have singlets, but you don't find them in the non-supersymmetric heterotic string case. Other than that, the spectrum match perfectly, and I think this is the best example of a string-string duality so far. So I think it's very likely that these two theories are strong, weak dual. But then not all the mass spectrum is preserved. You have some singlets that are not in one frame but are in the other. And so if you have a proposed map that will connect the different theories, it will depend on the duality frame. So that's very different from the supersymmetric case. On the other hand, you can extend this to type 2 constructions because you can play a game where here, let me show you here, you can then exchange this O7 minus for an O7 plus. You can do also here and you reduce the rank, but that's not heterotic. That's type 2. And so that's very nice because it allows you to extend the classification of heterotic strings you connect them with type 2 strings, so you have a bigger picture. And even more so, this, I think, gives evidence to the fact that strong weak duality makes sense in a supersymmetric string. So perhaps the ones that were proposed, they are actually good. And at least, but in this case, at least for freely acting orbitals. So you could have more complicated story. And another point that might be more interesting phenomenologically is that you have access to the potential to asymptotic regions of the modular space of this series. So maybe you can say something meaningful about the potential in the full modular space. So it's a bit more conjectural. So I'll just leave these things here. But let me first finish. So thanks for your attention. Let me just use this one too. Yes.
Thank you for the nice talk. So do you mind going back to the mapping with the duality? And you were saying that the fermions were different. What was the?
Sorry, what? In the non-supersymmetric case?
When you were there's a 7 case. You were saying that the spectrum is the same bosonic spectrum. And how did the spinors are the only ones that were different, right?
Yeah, the gauge bosons are the same.
And you're saying
so
that
the gauge symmetry is the gauge algebra is the same.
Okay.
But in the supersymmetric case, you have adjoint fermions because they are the superpartners. But then you break supersymmetry, and here the story changes. So here you still have O7-, and you put the difference on top, and you still have adjoint representations of the fermions.
Oh, I thought you said that they're different, the two duality frames, not different.
No, okay, when you break supersymmetry, you change the spectrum.
Oh, that's what you meant, okay.
But then in the two frames, they will be different just by the absence of a singlet. So it would be that you have a massless state appearing at strong coupling in the heterotic case.
Okay.
That's the same.
Okay, that's okay. Thanks.
I see Miguel.
Thanks for the very nice talk. So I wanted to ask the classification you have of bosonic CFTs, fermionic CFTs. The thing they have in common is that they have a current algebras that saturate the central charge of the CFT, right? That's how. So it's like you're classifying things which have a covering which is a torus, like a TN, or
yes, essentially.
That's the physics intuition of it.
Yeah.
Yeah, and also I had a question about what we was asking about the fermion singlet that appears or disappears. Can you see? I mean, that makes sense because like singlet fermions, they can get a mass, they can become heavy as you go to different corners of the duality. But it would be nice to see if you could like recover the mass term for it and see it appearing while limit term.
Yeah, no, I agree. That would be very interesting to understand. Thank you.
I can speak loud.
Okay.
Can you,
For the Zoom. It's for the Zoom.
okay. Thank you. So in these dual pairs that you discussed in the last slide, next to last, how do you get symplectic groups in the heterotic?
You get
because you can move branes wherever it depends. I mean, which planes you put, you can get orthogonal symplectic groups, as you said. But
yes, this already happens in the supersymmetric case in the CSR string in 8 dimensions. So, sorry, the question is how do you get them?
It's in heterotic.
In heterotic, it's because when you do the orbifold, you get when you look at the untwisted sector, you have short roots, but the untwisted sector can give you long roots, and then they can combine. And this gives you non-simply connected, non-simply laced groups. And in this case, it's symplectic.
Even in type 2, you can get this.
But here you are not doing all the using the classification.
Sorry, here? Yes,
For
the non-supersymmetric, I'm doing orbifolds. Yes. Right. Yes. So I use the classification. I have the classification, and then by hand I construct the orbifolds, and then I match the partition functions. So then I see that the classification actually works. But I have the orbifolds for the rank 8 rank reduced series.
Any more questions? Not then.
So they all have they all have tagias at some corner, right?
All of them, yes.
You couldn't find, okay, but does it have enough directions that I can potentially introduce it?
All of them have region. Well, E8 string has tachyons everywhere. A8 string. You compactify, you have tachyons everywhere. All the other strings, like this class 1 to A to B, they have regions with tachyons, they have regions without tachyons. So now the question of stability of those.
on the radius.
On the moduli, radius, Wilson lines.
Consider probably going to some point.
Yeah, you can go to a tachyon-free point, it's not a problem.
And this is a reduction of the E8, also has tachyons everywhere.
The reduction of the E8 has one tachyon in all the moduli space.
Okay, so wait.
Okay.
Yes. Okay.
You want to tell me when you have 5 minutes left?
Yes, but I think it will be finished before. Thank you. Oops. The other side or? Does it work?
So, next speaker is that Israel.
Okay, so first, thanks a lot, Mariana, Alvaro, and Nico for the invitation to give a talk in this very nice conference. So today, in accordance with the title of the workshop, I will tell you something about deconstruction, at least partially, of the heterotic flux landscape. So this is based on work which is in progress with Ilarion Melnikov, Ruel Minassian, that you all know very well, and Jan Proto, who is currently my student, and by the way, who is on the postdoc market and who is doing really very well. Okay, let me start with an introduction. So I thought before the conference that heterotic tricks deserved to be motivated because after all, it was something that was at the center of focus in the 80s, so it looks a little bit old-fashioned now. But we have seen in the very nice talks of Hector and Jorge that there are still many interesting things and things that we didn't expect to find in this context because it has a very rich structure. Okay, so in the 80s, people were interested in finding a phenomenological model from string theory by looking at heterotic compactification on Calabi-Yau manifolds with some Hermitian-Yang-Mills gauge bundle. And as you know, this is plagued with the problem of moduli. And so even in this nice and old context of heterotic strings, there is still room for fluxes. And this is what I will talk about today. And it's a little bit different than other type of flux compactification for several reasons. And I will first give a very short review about the feature. So these are just the generic heterotic compactification in 4D that can be understood geometrically. So they are worthwhile discussing. And but the problem is that we don't have many classification tools for them. Why? Because we lack all the nice theorems that we have for Kähler geometry, the Yau theorem that tell us that there is a Calabi-Yau metric, which is Ricci flat, the Donaldson Uhlenbeck Yau theorem that tells you that under certain conditions you have a connection in a gauge bundle that respects Hermitian-Yang-Mills, so we don't have anything of this sort in this case because the geometry is generically non-Kähler. So this is the first characteristic. So we know only, at least for minimal supersymmetry, very little of it. And also because the way the free-form flux is implemented in the equation, you will see, there are always cycles in the geometry that are string scale. So it's not so obvious that you can really make more sense of supergravity in this context. But fortunately, because it's heterotic, you only have flux for the free-form H and for the gauge field. So in principle, at least, you could use the worldsheet method and say that you have some 0,2 superconformal field theory on the worldsheet that you could relate to some nonlinear CM model with some target space of this sort. Okay, so there is essentially, even if this object at least is known for years, one class of solution that has been constructed so far, not more, that are principal T2 bundles over K3 surfaces. So they were originally motivated from M-theory duals, but there have been a lot of work about this from that period, and they preserve at least 4 supercharges. And the point is that, unlike what we expect for general heterotic flux quantification, the torus part, the fiber is small, string size, but the K3 base can be as large as you like. Okay. So there are generally K4 supercharges, but there is a subcase that I will discuss in more detail, which preserves actually 8 supercharges. And in this case, it's even believed this is a paper of Hilarion, Ruben, and Stephen Steigen, that they exhaust just all possibilities of 8 supercharges compactification of heterotic strings, which includes, of course, the trivial fibration, which is just K3 times T2. So I told you that there are potentially worldsheet model. In this case of model with 8 supercharges, there are. They are not properly superconformal field theory, but UV completion of what we believe are nonlinear sigma model on those geometry, which are kind of variants of the usual gauge linear sigma model. And what's nice with those type of tools is that if you have quantities that are protected by supersymmetry, you could compute them exactly. And this is what we did a few years ago in order to get, for instance, the exact form of the threshold correction in this torsional background. So one point of view that Ruben likes a lot is saying that because the base can be as large as you want, you can just decompactify the theory and view the theory as a compactification of a certain 8-dimensional theory, in which of course all the Narine dualities that we have heard about already today plays an important role. Okay, so the original goal was to explore in more detail the detail of the topological details that could enlarge a bit our understanding of this model, especially for 8 supercharges, because we think that they are just the whole landscape of compactification. But in the meantime, probably because I agreed to give this talk and the course of the workshop had to play a role, and so we discovered that instead of enlarging, we just maybe killed a large part of this moduli space for a reason that I will explain. And this will be the main point of this talk, just to tell you that there are ways to relate flux compactification to some that are non-fluxed. Okay, so I will start with some review of facts that are probably well known of some of you, or maybe many of you, about the geometry of topology of those heterotic compactification. After, I will make a bridge with things that we have heard already today in the previous talks, which are Narine lattices and some things that we didn't hear about, which are rational CFTs that play an unexpected role in this story. And after, we will see what things can happen in those flux vacua using this presentation of the fluxes. Okay, let's start with a review of known and old facts. So actually, the context in which we should study those flux quantification is known for many years. So Chris and Andy told us what to look for in the 80s. So from the covariantly constant spinor for this connection with torsion on your manifold, you can extract an SU3 structure, which tells you that you have a complex manifold with a 3-0 form and a 1-1 form that obeys those conditions. The manifold is not Kähler in general, but it obeys a weaker condition that you got from the De Latino variation, which is conformally balanced. And on top of this, because it's heterotic, you have also to say something about the gauge bundle. It has the connection of the gauge bundle has to obey this equation, which is the zero slope limit of Hermitian and Mills. So this is the data of your compactification, but these things are not independent because they have to obey some anomaly constellation condition, which is the Bianchi identity, okay, which relates the exterior derivative of H, which is present whenever the space is non-Kähler, with those traces which involve the curvature of the gauge bundle and some curvature of the tangent bundle. And it turns out that if you choose the right connection on the tangent bundle in this Bianchi identity, which is a Hull connection, this and that imply the equation of motion, at least at order alpha prime. And the tricky point here is that the problem is that mathematician plays a lot with this system, but they don't answer the question that we want to answer because they essentially try to find exact solution of this system. But the point is that both the equations are approximate. There is a well expansion at alpha prime, and the solutions are also approximate. So in some sense, you have to expand both and to check whether at the right order you get what you want. So for this reason, the mathematical literature about those solution is not so helpful for physicists, and we are still back to our old friend, which is this torus vibration over K3. So now it's time to present those geometries. So you start with, of course, a K3 surface, and you pick in the cohomology, you pick two global one form on your total space of your vibration, and such that the exterior derivative of this one form, of each of them, correspond to some integer class in your second cohomology. So you start with two classes, you can take them independent if you want to be generic. And then you want to use them to construct your vibration. So you choose for the moment freely the moduli of your torus, a complex structure and a complexified scalar, where B is a B field and this is the area. And so you group this one form together. And from this, you can build just your three structures that I mentioned before. So for instance, for the 3-0 form, you start with the 2-0 form on the K3 surface. You take the product with theta, which is homomorphic, and you get a 3-0 form. And the same for the 1-1 form, you just add this piece which corresponds to the contribution from the torus fiber. So it's not always the case that it defines the necessary structure. You have to ensure that F, which is F1 plus tau F2, where tau is the complex structure of the torus, shouldn't have a 2-0 component. So this is what we assume, no 0-2 component, sorry. This is what we assume from now, of course, because we want supersymmetry. But there is an even refined case that you could look at if on top of it also the 2-0 form is vanishing, which means that you just have 1-1 curvature, then you preserve not only 4 but 8 supercharges, and again this is what you expect to be the generic case of 8 supercharge compactification. So then you have to tell what the bundle is. So something that obviously works is to take the connection Hamiltonian connection on some bundle on the base and to pull back it to the total space. But you can add something and it will play a crucial role, which looks a bit like a Wilson line. So it's linear with a constant coefficient to one of those one form on the total space. So for simplicity and because we want to exhibit some dualities, we assume that the bundle that we have here on the base is abelian. And otherwise, you may think that you start with a general bundle, and by moving into moduli space, you reach a point where you have abelianized everything. And this is the context that we will consider. Okay, so you still have to solve Bianchi identity. So you do have non-trivial edge flux here. So it has several pieces. One that we call horizontal because it just lies on the base, and one that we call vertical because it has one leg on the fiber, and it's proportional to this piece where this is a constant metric on the torus fiber. Okay, so Bianchi is essentially given by these conditions, which tell you roughly that if your gauge bundle is too small, you don't have enough instanton number, you can compensate by the fibration essentially. So you cannot have a contribution of the fiber which is as big as you like. You just replace instantons by a contribution of the fiber. So because you have flux, you may ask whether there are quantization conditions, and here it's a bit subtle because H is not closed, and this is very important for the following. So this is something that has been obtained again by those gentlemen that I mentioned already, is that if you take the B field and you expand it again in a part with no legs on the fiber, one vertical with one leg, and a part which is just a constant B field on the torus, you can take this part, you refine it by shifting by this term, which again A should be thought as kind of Wilson line. This part transform exactly as a connection on a line bundle, which means that you have the corresponding first class that should be quantized. So it gives you a class here, which is a combination of the omega which defines the fibration. So omega was previously this Fi over 2 pi, and it's a combination of this and the data of the torus metric. So this is a familiar metric for a Wilson line on a torus, which is not fibered, with also B field. So this has to be quantized. And it's very suggestive to put all this topological data in a single vector, Okay, so I consider these vectors. The first two entries are the two classes that define my fibration. My two second entries are the nu I here, which are these classes that should be quantized as well. And then I have all the classes corresponding to the abelian gauge bundle. So it fills a vector of gamma 2 plus 16, understanding that each component is not an integer, it's an integral form. Okay, and the Bianchi identity can be just recast as this, where this bullet product is just a composition of the inner product on the Narine lattice with the natural product on the second cohomology lattice. Okay, so this brings out to Narine lattices because it seems that there is a very strong relation to gamma lattices, Narine lattices with this signature. So let me start by some generalities about those lattices. So I take a vector in this lattice, which is in fact the 2,2 lattice of the torus plus 2 copy of E8 of the E8 lattice, and I can expand as usual in terms of winding and momenta plus lambda, which is the weight in the E8 cross E8 lattice, and I use this metric to contract vectors. One question that you may ask in a CFT. In at least one or two dimension is the following. If you have a toroidal theory, under which condition you have an enlarged algebra, meaning that you have more chiral current, chiral operators than the current, the x1, the x2, and so on. And for this, you need to solve the condition that, for instance, the right momentum has to vanish, and you ask that the space of solution has rank 1, rank 2, or whatever rank you want. So in this case, if you take a T2, if you ask that P right is 0, you find that the momentum has to be related to the winding and also to the vector in E8 cross E8 in this precise way. Okay, and this, of course, is exactly the same as this condition on the quantization of the class, which means that it means two things. First, that the quantization condition of the heterotic flux background is equivalent to saying that at least when there are no Wilson lines, that the torus has to be a rational CFT. Why? There is no obvious reason, because we don't have a worldsheet description that would involve those extended algebras that you arise on the worldsheet. Okay, so this is the first point. The second point is that this vector here, there theory that we have, we should think of it as a vector of the left lattice, which is again non-empty in this case because we have the moduli of a rational CFT. So one other thing that you can play with null lattice is to perform, of course, dualities, which are lattice automorphism. Okay, and see what they mean in this context of fluxes. So among the lattice automorphisms, there are just few of them that will be of interest for us. The first one are just the generalization of the usual T-duality. You just flip winding and momenta around one circle. The second one is proper to 2 dimension and more. It just amounts to shift the value of the B field by some integer. And the last one, which is the most interesting in this case, because it really relies on the asymmetric nature of the heterotic lattice, is the Wilson shift, when you shift at the end of the Wilson line by some vector of gamma 8 plus gamma 8. So this is a transformation on the momenta that appear in P, but on top of this, you also have, of course, an action on the moduli themselves of the toroidal CFT. For instance, the factorized duality start from this data, radius and Wilson line, and end up with this data. And together with this, there is usually a phase that is carried by this symmetry when you act on the vertex operator of the CFT. Okay, so this was for toroidal theory. So why should we think that it's a good idea to apply this to the formal vectors that we have to define the flux background? Several reasons. First, I mean, the fiber is nowhere degenerate, so you may think that Bouchard rules apply without any obstruction. And in fact, the topological implications were studied by these people some time ago. And Ruben, with him, was the first, I think, to realize that you can also use other kind of duality, which are not just duality of T2, but of the world Marian lattice to change the topology of the space. And also, to be even more sure that these are valid symmetry, you can start, and this is something that I did 10 years ago, you can start with the gauge linear symmetry model description of those background and perform duality à la Boucher, which tell you that it's not only a symmetry of the infrared limit of the gauge linear symmetry model, but it's an exact symmetry of the model even in the UV. Okay. And it's also, so I won't speak about the index by lack of time. So now we will just play a bit with this and see what we get and what we learn about those background. We will start with something very simple, 5-dimensional BACUAV, in the sense that you just fiber a circle over your K3 and not a T2, and to see what you get. So we have a circle bundle over K3, and in this case, you just have a unique class which defines your fibration, and we write it like this: some integer h times omega p, where p is primitive in the lattice of the second cohomology. Okay, so in this case, you have a single quantization condition, which tells you essentially that your radius improved by the Wilsonian contribution here is quantized. It should be rational, okay? And you solve this for some integer that we call L. And so you have this value of the moduli, and you have this type of vectors that define your quantification. And this is a vector on which you can act with your dualities. A is a Wilsonian parameter. It's a vector, sorry. So one thing that was not known before also is that those spaces have a topology which is richer than expected. They are not simply connected, and pi 1 of the total space is given by the h, where h is this h which appear here in the anomaly constellation. Okay. So now we want to play a bit with the duality. The first one is the factorized duality, which is the usual duality. It doesn't do something so spectacular, so it will just flip those two classes. And I forgot to say that I chose a model with no gauge bundle at all, which is allowed in this case because you can just, the Auwager term can be compensated only by the torus bundle. Thank you. And so you will have something which is kind of expected, but what's interesting is that the pi 1 now becomes ZL instead of ZH, so you just flip the integers that appear in the two entries. So the most interesting duality, and this is where the deconstruction part arises, is what we have called the unwinding duality. So it works well if we start with a model with h equal 1, which means a simply connected flux quantification of this sort. And then we do a combination of a Wilson-like shift of parameter k, where k again is a vector, 16-dimensional vector, and a factorized duality. So we reach this vector together with those values of the radius and the Wilson line. And so the point is that you can always choose a vector k such as this vanishes. And when you do this, what you obtain is not a flex background, but an ordinary K3 times an S1. So you have converted your flex background into an ordinary K3 times S1 with some extra line bundle that you have here, which is not orthogonal to the Wilson line. So this is the particularity of the background. So you have K3 times S1 with a particular type of gauge bundle. Okay. This is, in some sense, interesting. In another sense, disappointing because we have killed some of the flex background that we liked. So this was for simply connected ones. For some non-simply connected ones, things are a little bit more complicated. So when the radius is rational, it was h over L. You can start with a parent theory, which is simply connected with L tilde equal LH. And you can get the theory with rational radius by doing just a shift orbifold, as you would do in flat space. And when you do this, you end up with a theory which corresponds to these vectors that you like. So what you may ask is this unwinding duality that you have done in the parent theory, which is simply connected, what it becomes in this theory. You just have to trace what happens to the to the transformation that you applied after you apply the orbifold, and you find something which looks like this. which means that you indeed have something that is like S3 times S1, which is true, but on top of this, you have an orbifold action that is not just a stupid shift orbifold like this, but something more complicated, because you combine a winding shift with a shift in the lattice of EL cross E8, okay? Which means that you have the choice either to have something which is geometric but with flux, or something which has no flux, it's just K3 times S1, but quotiented by a non-geometric symmetry. And also you have many variations of this game because pi1 is non-trivial, you can also do a CHL-like construction. And also they have duals on the unwound side, which have also non-geometric actions. Okay, so this is for the 5D case. I will very briefly say what happened in 4D. So it's almost the same, except that you have, of course, more possibilities. So you have quantization condition, as I told you, which tell you that your T2 is either rational or I would say half rational because it has chiral coherence, but it's not a fully rational theory. And now you have a vector with two primitive forms here. And you also, again, can do dualities of the same sort by combining factorized duality with Wilson line shift, such that by choosing appropriately your Wilson line shift, you can just kill the duality. So thank you. The idea is that you start with, this is an assumption, you start with any background of this type, you go to a point in the moduli space where the bundle is abelian, and then by duality you can just unwind everything. The price to pay may be to have those orbifold acting non-geometrically. Okay, this I will skip and I will move to the conclusion. So we have found that we have some strong evidence that n equal to 2 heterotic flux background can be unwound to ordinary K3 times T2 vacua of string theory with some line bundle and certain Wilson line, which are again non-orthogonal to each other. And an important caveat of this procedure is that in many cases we end up with a non-geometric orbifold of this. So you can either view it as a caveat or something nice, because I like non-geometric background, so in some sense it's interesting to relate two different type of vacua. And along the way, we have found that there are many possibilities to construct CHL-like background because of the rich topology of those spaces. And something that I didn't discuss at all is the case of n=1 backgrounds. So they can be obtained in two ways. So either, as I mentioned in the beginning, you start with a curvature of the bundles that has 2 zero piece. And this is something that we are currently studying, and it shows us everything. In particular, the 2 zero piece doesn't move under dualities. So so the vibration cannot be undone in this case. And there are also ways to construct n=1 by taking quotient of the T2 vibration over K3, which are like Borsia-Voisin-Calabi-Yau threefold. And what's nice with the unwinding duality is that we may find a way to understand how to resolve those singularities without being in the non-Kähler context that we don't really handle very well. Okay, I think I should stop here, and thank you for your attention.
Thanks for the talk. Related to what was discussed before, would it mean from your conclusion that any heterotic compactification would be related to an orbifold of 10D heterotic somehow, at least connected to it?
What we say is that flux compactification with 8 supercharges can be related to orbifold of K3 times T2 compactification. But after we can move in the K3 moduli space maybe to simplify things even more.
This is what I'm asking, if I could go even that in that direction.
Yes, maybe you have to be careful, but because you had quantization condition in the beginning, but in some ways are not lost after the dualities. So they still occur in the gauge bundle sector somewhere. So you have to be sure that you can do wherever you want. Because you started with something with quantization condition, you end up with something that should have somehow similar constraint. But I understand the idea you want to go to K3 times T2, then to go to the orbifold limit of K3, something like that. Yes, maybe.
Should I?
What about spaces like K3 times T4 or something like this?
You can do the same because the structure of the fibration, yes, you
But,
can
but
do
it's the same
similar.
statement that the fluxes can always be unwound and pushed to a geometric or to a
We didn't
non-flux
study
order.
explicitly what happens, but I'm not sure qualitatively it's that different. Probably you can do similar tricks, but it's just an assumption.
And one quick announcement, we're gonna take the picture right now before the coffee, so just everyone please go to the front door now and then get free to get the coffee.
No, I cannot hear you. Can you hear me? Alvaro, can you hear me?
Salvatore, can you hear?
Now I can hear you. Can you hear me?
You should be able to hear. If you can, write on the chat.
Um,
Can you hear us, Salvatore?
Testing. Testing.
I can hear you, but is it?
but can you hear me?
From that,
Can you hear me? No, we cannot.
Ah,
no.
Tu l'as?
C'est ça?
Speak, Salvatore.
yes. Can you hear me now?
there.
Yeah, but it's okay.
Okay.
Say something again.
Okay. Can you hear me?
Yes, Salvatore, speak.
Yes. I'll keep talking until until you tell me. Can you hear me? Can you hear me? Can you hear me?
Ouais, super, donc on part.
Can you hear me? Can you hear me? I guess you cannot.
Can hear you. We can hear you.
You can hear me, okay, but there's some sort of weird return when you speak.
Okay. Hey, Salvatore?
Yes.
You can hear, right?
I can hear you. The question is, can you hear me? I mean, I can hear you, not always, I would say. Because if you now were saying something, I was not hearing you.
Now it should work correctly.
Maybe, can you use the box? to use the box instead of the microphone.
You should turn it down. You should use a cask, not the speakers, like headphones.
Okay, now it's clearer.
Can you do that?
Tell him that we cannot hear him now, that he has to communicate through chat, please.
Yeah, you should. I will not hear you because we are turning on off the speaker because, yeah, but that's intentional. Don't worry about that. Just use headphones or something.
And when they are ready, tell us, and then we will.
Yeah, when you have the headphones, there should be no problem with the sound. So we try again. Let us know in the chat and we try again. So when you can, try to put up the slides and the video so we can start testing that.
I couldn't hear what you said. It was super unclear.
You can hear now?
Yes.
He's hearing.
You can hear or not? Yeah, what it's going to do is with all the time, with every question.
No, but now it's just to check that he has the headphones, and this is to check that he has the headphones, and then if he can, like, he couldn't hear you on the first time when you told him to share the slides. So just repeat the message, like, whenever you have the headphones, please let us know and share the slides and the video.
Salvatore?
Yes.
So we are trying to fix the sound, but for now, put the slides up and your video up so you can test that as well.
Yes.
Please.
Yes.
Okay, it seems to be working, the slides. We're trying to fix the sound issue.
Now maybe if you can try to get some headphones or something.
Okay, did you hear me before? Can you get headphones?
I can try. Give me 1 second.
Because the problem is that it comes back in your own speakers.
Is it better now? Is now better?
Sorry, can you say it again?
Now, can you hear me?
Okay, let's... No, let's hear it down, sorry. Was it?
Yes. Can you hear me? I guess you cannot hear me.
Salvatore, we can hear you. The problem is that basically whenever we have the speakers to hear you and our mic on at the same time. There's this weird reverb. So basically, we're trying to fix that. I don't think it's from your side. The thing is, we're trying to fix that. Maybe what we will have to do is to basically turn off all the mics here during your talk, and then whenever someone asks or something, we will have to turn off like your volume when they are asking, and then turn on your volume when you reply. So basically, we should try to avoid that the two of you are speaking at the same time. Is it working now? Wait. No. Okay, yeah, I think that's the status, Salvatore. We will probably have to do it like that.
Okay.
But we have like 3-4 more minutes, so we will try to fix that. But if not, we will have to do like that. So, yeah. Can you talk?
Yeah. Can you? Yes, it's fine. It's fine. Yes.
Okay. Yeah, no, I mean, yeah, we can hear you, but it's still the same problem.
Yeah. We have to do like you said, probably. But I'm sorry if it's too much of a hassle. We can give up. We can, if you want.
We couldn't hear you, sorry, because we were testing the mic and we had to like. Sorry about that. Let's say. Hold on a minute. Okay. Hello, is this working now? Salvatore, can you hear us?
Yes.
I know, but we are outside the Zoom. No, are we on Zoom?
I can hear you.
Are we? Okay, so Salvatore, just hold on. We cannot hear you now. I mean, again, we cannot hear you now, but intentionally. Okay.
C'est un problème.
En fait, il y a des échos. Il y a des larcènes.
Sí,
Oui, parce que toi,
c'est le micro là.
Si je parle ici, c'est... Ouais. Allô. Sorry, Salvatore, we are testing.
Si le son, c'est lui. Il y a une source de son.
C'est le output.
Non, mais là l'output, faut le laisser sur.
Esto está bajado, ¿no? Esto está bajado.
Attends, mais t'as quand même du. Oui, il est à 0.
Là, je fais mute, non.
Non, il est pas vrai. Oui.
Hein?
Non, ça c'est l'output. Fais-le input à 0 complètement sur celui-là. Non, là, tout en bas.
Testeado, ¿no? Ellos, quiero decir.
Por eso le voy a hacer. Toma a 0, là.
Estate para sube y vamos probando sistemáticamente porque o cuando digan.
Il faut vraiment à 0.
Salvatore, we keep working. Just hold on. Okay, yeah. I see you nodding. So okay, thank you. Is it up? Okay, Salvatore, can you try to talk now? Just
Okay, I am
for a second.
talking.
Speak.
Yes, I am talking.
Okay,
Can you
okay.
hear me?
It's we're still having the same problem.
Okay.
Non, c'est normal. Là, en fait, c'est en Zoom. Donc là, c'est le micro pour la session Zoom de là. Et c'est lui qui l'écoute à distance.
Oui, mais lui, il devrait pouvoir parler, on l'écoute pas ici.
Oui. Bah, c'est on l'a tout à l'heure, ça, avec le... On l'a bien, mais c'est le problème que c'est le son est pas bon, c'est ça.
Mais s'il parle déjà, c'est le volume, c'est et là-bas c'est.
Okay, Salvatore, please try to speak now.
Yes, now can you hear me? Can you hear me now?
Keep going. I think we cannot hear you. Just say blah 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 or whatever. No.
Blah 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 blah.
Yeah, no. Okay, it's not working. Sorry. Hold on. I mean, I will keep asking you to talk every now and then until we fix it. Sorry about that.
Vas-y, retourne dans ta session Zoom longue, il y avait le mec en photo.
Okay, can we try to speak now again?
Yes, now can you hear me? Can you hear me well?
No, they're not working. I mean, they're trying to change like the output. No, and hello. No.
Hello. Can you hear me?
Okay, right. So now you hear us and no. Okay, hold on. Sorry, I'm talking to you and at the same time I'm talking to the IT people. Sorry.
Ouais, ça marche. Oui, mais ça marche, mais ça devrait renvoyer. C'est ça qui est cassé.
Il y en a
C'est ça qui est
là-bas
cassé.
dans mon bureau.
Eh ben, prends-le parce que c'est ça qui est cassé à mon avis.
Okay, we think we found the problem. Now we have to fix it, but I think this.
Ouais, mais tu vois, on entend très peu. C'est ça qui est bon. Mais en fait, ça explique pas le lancer.
No, but still, I hear myself there, right?
Déjà, ça marche.
Pero sigue habiendo interferencia.
Ah, non.
Oui.
Alors après, peut-être comme il ne marchait pas, on a mis un son. Du coup, il y a le lacet.
Entre esto y eso.
C'est mort.
Porque si yo hablo a eso y esto está de output,
Si, c'est ce qui va en faire.
lo que sale aquí entra aquí.
Necesitarlo si tiene un teléfono de vídeo. Si no está los...
Okay, Salvatore, hold on. We are testing something else. Hola. Hi. Hello. Trying, testing.
Yeah, but there's still the river, right?
Okay, sorry.
On va les entendre là aussi. Là, il y a Zoom. Il n'attrape pas besoin.
Si tu veux, on peut réessayer.
Salvatore,
Yes.
keep speaking.
Okay. Okay. Can you hear me? Can you see my pointer?
Yes.
Yeah.
So keep
Okay.
talking.
Yes. Okay. Keep talking. Hello. Hello. Hi, Alvaro.
Yes. Yeah. Yes.
On peut descendre un petit peu.
It's a yes. It's working. Is it working finally? Okay.
You can hear us, right? You can
Yes,
hear
I
us.
can. I can
Okay.
hear you.
It's working. It's working.
Thank you so much, guys. Thank you so much.
No, don't worry. Please don't worry. I'm sorry about the whole delay and so on.
You can already tell them.
This is the one I will pass.
I think we should try to only work with. Well, no, let's try.
Okay, trying.
Okay.
Yeah. Okay. You can hear two different people. Can you see us? No,
Nice.
see us. I don't think he will see us anymore.
No, I cannot see you.
No, but you can hear. Okay, you could hear Alessandro and you could hear me, right?
Yeah. Yes.
Okay. Perfect. I think we're good. Right, yeah, if you don't mind that you don't see the people, because that would take an extra 15 minutes probably. And
No, it's fine. I know half of the people there, so I might probably recognize all the
we can
voices.
to like when like in press conferences to say the name and institution or something like you know. I will call. Yeah, I will call the people.
Please state.
Right, just hold on. We're gonna call the people and then we will start. Okay, Salvatore. Salvatore, can you hear us now?
Yes.
Okay. We have
By the way, can you see my pointer?
we can see your pointer.
Great. Okay. Oh, I can also see you now. Well, some of you. Okay.
Yeah, we can see the pointer.
This switches on automatically when you pick it up.
Exactly. So, and that one basically, when you introduce him, just turn it on and then turn it off, and then whenever you want to speak, turn it on again. Okay, so now you should be hearing us, and yeah,
Yes.
Alessandro is gonna try the other mic. Yeah, you're hearing, bro. Okay, we'll start in a couple minutes. In 1 minute, people are getting into the room. Pero sacamos. Wait, hold on.
Salvatore, ¿puedes decir algo? Can you say something?
Yes. Hello.
Okay, yeah, okay, we'll just wait for a second. Okay, everything should be okay now. Alessandro will be the chair.
That one we have to leave it there.
Okay.
Because otherwise, I mean, it turns on.
Okay, welcome to the last session of the workshop. The next speaker is Salvatore Raucci from Scuola Normale, who's going to tell us about charting the landscape of non-supersymmetric strings. And one thing, if you want to ask any questions, please remember that we need to speak into the mic, otherwise Salvatore will not hear us. And one more thing, he cannot see us. So state your name and institute. Okay, Salvatore, please.
Thank you, Alessandro. So first of all, I want to apologize for not being there with you at the moment, and also I want to say a good thank you to the organizers for, first of all, for setting up this incredible conference, and then for allowing me to do my talk on Zoom. So back to the talk. So one of the topics of today is non-supersymmetric backgrounds, and in some sense you can rephrase non-supersymmetric backgrounds, I would say, with charting the landscape of string theory without space-time supersymmetry. Now, if you look at my title, it's quite that, but there is a difference, because my title is charting the landscape of non-supersymmetric strings. And so this landscape, the one in my title, is a sub-landscape of the landscape of one of today's topic. So the first thing I will do today is to try to connect the two landscapes. In a sense, I will try to tell you why I think it's important to understand the landscape of non-supersymmetric strings as a first step towards understanding of the landscape without space-time supersymmetry in general. And then I will introduce these non-SUSY models, which already appeared in other talks and reviews. And after this, I will move to the main body of the talk, which is to discuss, first of all, what you expect to obtain from these non-SUSY strings. And then I will tell you some flux compactifications that we have. These are these Freund-Rubin vacua. And at the end, last 5 minutes, I will discuss a possible approach to systematically investigate the landscape of these theories, which is still some work in progress. So let me begin with some context. So the context in which you have to understand this talk is that we want to find geometric string vacua without space-time supersymmetry, which are in some appropriate sense under control. And I want to stress that the keywords here are geometric. By geometric, I mean I will only discuss vacua that are 10-dimensional geometries. I will not consider any stringy sector or alpha prime or directions with alpha prime length, let's say, but I will discuss full 10D target space with some Riemannian geometry. And second, under control, I will tell you what I mean by under control in a couple of slides. So here, the subtle point is the absence of space-time supersymmetry. And just to list what are the subtleties and the issue that you encounter when you abandon space-time supersymmetry in string theory, I'm listing 3 here. One is that you have a limited set of tools to explore your landscape. That's because most, if not all, the tools that we have in flux compactifications are based on space-time supersymmetry. Then, when you don't have space-time supersymmetry, you have a limited control, in the sense that you have quantum corrections, and quantum corrections will generically appear for everything, and you have to be careful whether your vacuum, your solution, will survive after quantum corrections. And third point, which will not be one of the main topics of today, but just will appear over and over, without space-time supersymmetry, you usually get some generic instability, because there's no reason why you should have something stable, and reason is usually supersymmetry. So without it, you generically find instabilities. But the real question here, I think, is how could we chart then the non-SUSY landscape? So here I mean the generic landscape without space-time supersymmetry, and I want to stress the how. How can we do it? If we don't have these tools, we don't have control, and we always find something unstable. Well, since we are studying string theory, we have an answer from string theory. And it is not the best answer probably, but the answer is, well, you get the equations of motion from string theory, and the equations of motion are really the connection between the worldsheet and the target space. Now, the equations of motion from string theory generically are a double expansion in G string and alpha prime. With G string, I mean e to the phi. And therefore, the low energy effective action for the massless modes of the string that you expect to have from any string theory will take this form. It will be a double expansion in e to the phi and alpha prime of some operators with mass dimension 2 plus 2m. Now, what happens when you have spacetime supersymmetry? This will be important at the end of the talk. First of all, you don't have to consider this double series because many of the terms in the actions are protected. For instance, if you take 10-dimensional string, the spacetime supersymmetric 10-dimensional string theories, the two derivative action of the 5 superstring theories are the actions from supergravities, from 10-dimensional supergravities. So this is to say that the e to the phi series is truncated at the 3 level. Only the 3 level contribution enters at the 2 derivative level. And so you have a huge simplification here because one series here in G string is truncated. But you don't even need to solve the equations of motion because it is enough to require unbroken supersymmetry. So to solve for the supersymmetry variations equals to 0 to obtain a solution to the equations of motion. And the SUSY equations are first order equations. So it's simpler than to solve the second order equations of motion. And furthermore, they are spinorial equations. And with spinors, they're written in terms of spinors, and with the spinors, you get access to more structures on the manifolds you consider. So with equations of motion, you can only control the Riemannian structure. With the spinorial equations, you can control, for instance, the complex structure, the Kähler structure, and so on. And last point is that spacetime supersymmetry is a dynamical abstraction to the case, and without it, you lose any dynamical abstraction. You can still get some topological abstraction, but no dynamical abstraction. So let me be explicit once here to give you a flavor of what I want to say. What you expect from string theory at the 2 derivative level is such an action in which you have the usual operators R, d phi squared, fluxes, and in front of each of them, you would expect to find a series expansion in G string. So it's a minus 2 phi plus corrections. And here I'm writing only the first one loop correction for closed strings. But in principle, you might get something more. You might have some other operator, this lambda, which you should read as an operator, not as a constant, which was 0 for 10-dimensional supergravities. And so this is really the important guide that you have to take into account if you want to study supersymmetry breaking. Let me add a couple of comments on this action. Again, this is fine as a perturbative expansion in G string in all terms except this lambda. Because, let me tell you again, you have to compare it with 0. It doesn't mean that necessarily you will not be able to treat lambda as a perturbative parameter. So it doesn't mean that you won't be able to start from some solution and then add lambda perturbatively. But generically, you expect that generically you will not be able to do this, to treat lambda perturbatively. And the second comment, which is not connected to the main line of thought of this talk, which is something that you can discuss later in the discussion session, is the question that arises all times that I discuss these topics with people. And the question is, we know this from string theory. Now, is there a low energy principle, and you can read here Swampland condition or whatever you want to read here, which could explain these types of corrections, namely that the corrections are rearranged into a series in e to the phi in front of the operators. And even more importantly, which is that a low energy principle which could predict the possible form of lambda, the possible dependence of lambda on the fields. This I don't know even how to approach this question, but I think it's an interesting question. Just from consistency of quantum gravity, whether you can say something about this lambda when you don't have spacetime supersymmetry, but still you have a consistent theory of gravity. But the question that will lead us to the non-SUSY string is that can we have control on lambda, so compute it and really know where it comes from string theory? And well, we can. And the main example in which you can compute it and have exact control on what it means in string theory is non-SUSY strings. Of course, you can also say that if you take a Scherz-Schwarz compactification, you also have control. That's true. But in some sense, these are the most basic and zeroth order settings in which you can control lambda. So in a sense, they're the simplest settings in which you can control lambda. So let me briefly introduce these theories that have already been mentioned in other talks. There are three known non-SUSY tachyon-free string theories in 10 dimensions, which are the theories I call non-SUSY strings. One is a closed string theory, heterotic SO16 times SO16, and two are open string theories. One is the Sugimoto or USP32 theory, and the other one is type 0 prime B string theory. And they are related to the usual 5 spacetime supersymmetric string theories in 10 dimensions by some operations here. In this talk, I will focus on the heterotic. I will mainly focus on the heterotic. I will say something about the others, but I will mainly focus on the heterotic also because other talks today have been discussing the heterotic, these or in general heterotic theories. So I think it's nice to see what happens here in the non-SUSY heterotic. So back to the lambda. What is lambda in these models? So lambda is in general a scalar potential for the dilaton, which is known as the Tatwell potential. And it corresponds to adding this term to low energy effective action. So some t, some number, some coefficient times an exponential of the dilaton, e to the gamma phi, with t and gamma which depend on the model. Now it is true that you can understand this addition to the energy effective action from spacetime, because it comes from some residual NSN extension. But what I want to stress today is that you can really have control on this term from the worksheet. And the reason is that these non-SUSY theories have infrared divergences. If you start computing amplitudes, at some point you will find infrared divergences. And these infrared divergences are due to tadpoles, to massless tadpoles. And it is known how to solve for these massless tadpoles. And the mechanism that solves it is known as the Fischler-Susskind mechanism and corresponds to shifting the background of the string. And the background shift that you need to implement corresponds exactly to adding this term to the low energy effective action. So you understand this from the worksheet as a way to solve for massless tadpoles. As a side comment here, notice that the effect of shifting the background is similar to what you would expect in quantum field theory. Because if you have tadpoles in quantum field theory, what you do is that you add a background field such that the tadpoles that you add through the background fields are equal and opposite to the tadpoles you had originally. And so here the punchline is the same, even though the mechanism is completely different. For the heterotic theory, the SO16 times SO16, this lambda operator is actually cosmological constant, even though it's a cosmological constant in the string frame. But what I want to say is that gamma equals 0. It has already been said a couple of times. And it also maintains the interpretation of a vacuum energy in quantum field theory because it is positive, which reflects the fact that the theory has more fermions. So your QFT, let's say, intuition is correct. The supersymmetry breaking or the absence of supersymmetry here adds a quantum vacuum energy, and this quantum vacuum energy is positive because you have more fermions, even though, again, this is a quantum vacuum energy in the string frame. And the idea of this talk is that since we generically need to take into account these in order to chart the landscape, in order to find vacuum, then we can try to use these in flash compactifications to see whether we can get something interesting. So just to be specific here, this is the low energy effective action that you are led to take into account if you want to study classical vacuum of non-SUSY strings. So you have the usual operators here. This you have to take it as a leading order expansion in G string. So R, if I square fluxes with a generic dilaton dressing beta k, and this lambda operator. Let me just mention that for the orientifals, gamma equals -1, so this gamma here, and you have several cases for the k's here for the fluxes. In 0 prime B, you can have k equals 1, 3, and 5, and in Sugimoto, you only have k equals 3 with beta k equals 0 because they are Ramond-Ramond fields. And you also have gauge fields in both orientifals, so you should have the trace here in front of the F2 squared with beta k equals -1. While for the heterotic, which is the case we'll focus on today, gamma is 0, as I already told you, and you have two classes of fluxes. One is an SNS flux with k equals 3, so F3 squared, and beta k equals -2, and the other is gauge fields. So you should have the trace in front of F2 squared, and beta k is -2. a quick comment. These are not quite the right spectra that would allow you to treat this lambda operator as a small perturbation in vacuum, generically at least. There is a counterexample for zero prime string theory that you can read in this paper, and there are other examples for lower dimensional tadpoles. For instance, in these two papers, what the authors consider is a 9-dimensional tadpole. So one of their dimensions is stringy size, and the other 9s are extended, and the tadpole is in 9 dimensions. In those cases, you can treat with these spectra this lambda operator as a small perturbation. But in 10 dimensions, if you require full 10D extended spacetime, you cannot. So you really need to take into account this term, this tadpole potential in your flux compactifications, for instance. So the first question that you might have, or that I do have, is what should we expect? Now, this has been already mentioned in other review talks, but there is a generalization of the Maldacena-Nunez-Nogo theorem for these non-SUSY strings, which tells you that you cannot get the Citterer-Minkowski by just adding these tadpole potentials with these values. And this has been done by Ivano and Stefano some years ago. Let me just mention that you can do something similar for the scale separation. You can run an argument similar to the one that Thomas showed us in the first day, referring to Thomas' paper, and you can prove that scale separation here would require the same conditions as you have in the paper, which is large Diraton gradients and so on. But generically, you don't get any improvement in scale separation just with this tadpole potential. And plus, these no-go theorems can be avoided by the usual technique, by the usual mechanisms, either adding orientivals, so stuff with negative tension, or allowing for boundaries in internal manifolds. Because you usually integrate by parts, and you could get boundary terms from integrating by parts in the internal space. And let me just mention that boundaries here are particularly puzzling in these models because they already appear in the simplest, in a sense, types of solutions, which are the so-called Dudas-Murad solutions, which are candidates for vacuum solutions of these models. But I will not mention these anymore, just as a side comment. But so the punchline here is that you don't get anything drastically different from what you have in the usual 10-dimensional superstring theories. But still, you can get some ADSs. And a good question here, I think, is to try to understand which ADSs you can get. But here, again, remember the introduction, you need to solve the equations of motion. And it is complicated if you want to solve the equations of motion in general. So one idea, which is in a sense the simplest idea, I think, would be to balance the tadpole contribution, the scalar potential contribution, with fluxes. And this leads to Freund-Rubin vacuum. In particular, I will only tell you the story for the heterotic. If you turn on the F3 and SNS flux, you do get an ADS 7 times S3 solution with magnetic flux on S3. This has been found by Murad and Zagnotti in 2016. And this solution is perturbatively unstable, as is written here. But since you can replace S3 with any other Einstein manifold, M3, with the appropriate curvature, you might be able to get perturbative stability, and you actually do get perturbative stability by replacing S3 with RP3, with the projective space. And this has been pointed out in this paper, in which they also proved the perturbative instability. Still, this solution is non-perturbatively unstable by brane nucleation. So this would be fine for a phenomenology. Actually, it's not, because it's not scale separated, but still, you find what you expect to find, something which in some sense is always unstable. It is an open question, as far as I know, to try to classify all possible Freund-Rubin solutions in these settings, and I'm trying to work on this at the moment. And in the heterotic case, there is one case which is particularly interesting, I think, which is an ADS 4 times X3 times Y3 with two magnetic fluxes on X3 and Y3. This is present in Ivano's PhD thesis, actually, but he never really investigated whether this exists for some values of the fluxes, let's say, or whether there might be something interesting in this as regards to perturbative stability. But you can also take the k equals 2 case. Remember, for the heterotic, there's the k equals 3 and SNS flux and k equals 2 gauge flux. You can turn on a U1 gauge flux in the heterotic theory. And what you get is an ADS A times S2 solution with magnetic flux on the S2. Now, the stability properties of this are to me, they are a bit puzzling because this is stable under perturbations of the metric diaton and U1 gauge field that you turn on. But the perturbations in the mixed abelian and abelian gauge sector are complicated to solve, to understand. And actually, there are indications from the flat space limit that instabilities will appear in the mixed abelian and abelian gauge sector. And this will mean that this solution, this ADS times S2 will decay through, let's say, some non-abelian radiation, emission of non-abelian radiation. Now, honestly, I don't know how to interpret this instability, if it's just an unstable solution or if it has some physical sense. It is just, to me, it's just reminiscent of what happens for magnetic monopoles in Yang-Mills theories, because there you have only one stable magnetic monopoles in each topological class of the gauge group, and all the others decay through non-abelian radiation to the stable one. So it might be that this solution could represent some object, even though I don't know how, at the moment, how to check this statement. But the take-home message of this section of the talk is that it is possible to balance the tuple with fluxes and curvatures. And these simple solutions are, in some way or another, unstable. And this matches with the general issue of stability without spacetime supersymmetry that you expect. But what is true here is that certainly we are missing the right tools to address the problem, because here we are only, let's say, charting a very small corner of the landscape of these non-SUSY theories. We're just balancing tuples with fluxes and using a very simple Freund-Rubin ansatz. But can we do something better? I don't have a full answer to this, and probably nobody has a full answer to this. But this, I think, is the question I want to leave you with. What is some good strategy to, thanks Alessandro, I saw the message. What is a good strategy to systematically investigate the landscape? I want to propose one possibility, which goes under the name of fake supersymmetry. Now, the idea here is to mimic supersymmetry as a solution generating technique without any physics behind the solution generating technique. And in practice, it corresponds to defining two operators, dm and O, such that the two spinorial equations, dm epsilon and O epsilon equals 0, imply the equations of motion. And here you could take several spinors or more than two operators, but let's say generically some operators on some spinors equals 0, which imply the equations of motion. And this would mimic supersymmetry in the fact that these operators have to be first order operators, and the equations are spinorial equations. So let me state it again. This will be a solution generating technique, and in principle, there will be no physics behind these equations. This will not be variations of anything. Now, the question is this possible for non-SUSY strings? Turns out that for gravity and the dilaton, it is possible. And the simplest possibility involves, again, two operators with one spinor. And the two operators take this very simple form. D is just a derivative plus a function of phi times the gamma matrix, and O is d phi plus a function of phi. You can find these functions in the paper. It's not relevant for what I want to say. So it is possible for gravity and the dilaton. But if you try to plug in the ansatz for, let's say, the usual Calabi-Yau ansatz, you don't find any solution. And the problem here is some gamma matrix parity that goes wrong. So here, the significant progress here you would expect would be to add fluxes into the game. However, the simplest possibility to add fluxes doesn't work. The simplest possibility, I mean, just a linear combination of type 1 supergravity and this modification with W and G. You would expect this to make sense, because if you turn off the fluxes, you would expect to find again the previous operators. And if you turn off the potential in some sense, you would expect to find back the type 1 supergravity, operators. But this doesn't work. Now, this is not necessarily the end of the story, because you could try to change the spinor ansatz, and in particular, you can get something else by turning W into a complex matrix. But the story is way more complicated if you allow for a generic W and G, which can be complex matrices, and I don't know how to approach the problem in a sensible way. Another approach that was suggested to me by Alessandro, and I never really explored it, is that, remember at the beginning, without spacetime supersymmetry, you expect loop corrections. So in particular, all the operators in your low energy effective action will have a full G-string expansion. So it could be that adding some loop corrections would improve the situation here, because also the kinetic terms of the fluxes might be loop corrected and will be generically loop corrected. But again, this is an open question whether this could improve the situation here. A couple of subtle points before concluding. This fake supersymmetry approach mixes loop entry level effects, and so it is in principle dangerous. In fact, you can prove that with only gravity and the dilaton, the equations I showed you always have a strongly coupled regime, and so you cannot trust what you're doing anymore, at least in this strongly coupled regime. Second is that the equations are not necessarily unique because there's no physics behind. And in fact, already for gravity and the dilaton, for the heterotic, there are 3 sets of W and G which imply the equations of motion. And you have to decide which of the 3 makes sense for you. And this will probably be solved by alpha prime corrections or by loop corrections, but at the moment, again, this is something that needs to be understood better. So let me make a summary of what I did and conclude. So what I told you is that the importance of non-SUSY string is that you have control on what this lambda operator is. Then you can try to use lambda as an ingredient in flux compactification. And as again, I told you, there are no drastic changes, but you can get some solutions, some very simple Freund-Rubin solution by balancing Topple with fluxes. However, what is certainly true is that we are missing the right techniques to engineer vacuum in a systematic way, and fake supersymmetry might be one possibility to address this problem. But my conclusion is just one line here, is that for sure the landscape of non-SUSY strings remains largely uncharted. And I think the problem here is that we are missing the right techniques to do it, but that's important as a first step to understand the landscape of string theory without space-time supersymmetry. And with this, I thank you for your attention.
Any questions?
Hi, so I'm David Dendrio from LabTHNC.
I wasn't serious.
No, it's a very naive question. Since indeed we are missing techniques to engineer vacuum, how about numerics? Simply to at least get some solutions and maybe get some intuition on them?
Yeah, numerics are a way, for sure. But it will be some brute force approach in a sense.
Yes.
Hey!
Which is not necessarily bad, I mean, but still it's not satisfying to me, at least, as a way to say, okay, we solved it, we know how to approach the problem. But yes, numerics would be a way.
Okay, thank you.
Hi, thanks for the talk. This is Giuseppe Riditette from Rome Tor Vergata. You said it, now we do it. So I was just wondering in detail what kind of instability channel the ADS7 vacuum has.
Yeah.
You mentioned something about brain nucleation, but yeah, I was just curious.
Yes. So here the channel is the NS5 brain nucleation in the heterotic theory. So if you take this background, this is unstable by an NS5 nucleation, which reduces the flux, and the solution goes to the small flux regime after the NS5 nucleates.
He's satisfied. So while we are on this, no, wait, there was another slide. Then maybe I can ask myself. What about the ADS8 solution? What happened to that one?
No, for the ADS8,
Indication instability, and I mixed what you meant.
That just means that I was not able to solve for.
This is Alessandro Tomasiello from.
Yeah, I can this just means that I was not able to solve the equations for the linear perturbations here. But this means that if you take the large flux regime, which is the regime where the solution is under control, so a large magnetic flux on S2, this solution is nearly flat space. It's an ADS8 with very low curvature, and S2 again with very low curvature. It's close to flat space, and in flat space, the parameters that you plug into the solution, so the magnetic flux that you have, are such that this solution in flat space would be unstable by this mixed abelian or abelian radiation. This is what I'm saying. So I wasn't able to solve the perturbations in this sector, but indications come from the flat space limit in these two papers from the 70s, which tell you that there should be an instability there. This is what I mean.
What was the context?
Say it again?
What was the context of these two papers?
The context was to study strong magnetic fields in from U1
okay.
abelian gauge theory in flat space.
Okay, sorry.
Okay, Niccolò Petri, Ben-Gurion University. So, okay, maybe this is a silly question. Have you tried ADS9?
So ADS9 would be like ADS9 without fluxes, just ADS9 times something else.
Exactly.
Let me go here. So this goes back to something I didn't mention, which are in these models there's some literature on codimensional one solutions, which are known as the Dust-Monod solutions, which are flat space fibered over some other direction. Now, your question would be, what about ADS9s fibered over some other direction? You cannot solve the equations explicitly, but you could do numerics. So back to the first question. And numerics tells you that, yes, you could get an ADS9, but you would encounter divergences at the two endpoints of the other direction that you have. So you would have ADS9 times something, and this something will have divergences at the two, let's say, endpoints of this something. It will be finite distance singularities.
This would be like objects?
And that's the problem. Because how can you argue for objects here? There will be just wild singularities. There's no interpretation of these guys as objects. I mean, what happens for the Dust-Monod solution now is that also this solution is singular, and these singularities now are interpreted as end-of-the-world branes. Now, it could be that also for ADS9 you can interpret the singularities as end-of-the-world branes, but something that I always try to stress when talking about this codimensional one solution is that not all singularities are solved in string theory. Not every time that you find a singularity that's physical.
Yeah, this was an important topic of discussion earlier today.
Yeah. So again, until you get some stringy, let's say some stringy interpretation or understanding, I don't think it makes even sense to.
Careful, the man is here.
No, but he knows very well.
Okay.
Okay, thank you very much.
I guess the crowd spontaneously decided that your talk was over. So, Salvatore,
Yeah, I saw it. Okay.
With Salvatore, it's evening.
I will share the screen again. Just to avoid it.
I think we can begin the discussion session. Goodbye, Salvatore. No, she's like, okay, goodbye, Salvatore. Thank you for everything. And get well soon.
Thank you so much. Bye.
The panelists.